Yeah. So the second talk, yeah, please go ahead. The second talk is given by Max Ruttenberg, and the work is about beyond static parallel loops, supporting dynamic task parallelism on Manycore architectures with software managed Scratchpad memories. And this work is done by a number of authors from University of Washington and Cornell University.
Good. All right. Hi, everyone. I'm Max, with your PhD student. I'm going to tell you a little bit about a research project. This was a collaboration between UW and Cornell on supporting dynamic task parallelism on Manycores with software managed Scratchpad memories. So as I'm sure a lot of people in this room know, data-intensive applications are driving a demand for higher performance at lower power and cost. At the same time, the newer process technologies plus some great recent research and physical design methods have made it possible to place thousands of cores on a single chip, which is going to be really helpful for meeting these demands. But these chips have required some very big memory system redesigns. A major concern is that the hardware cache coherence that we knew and loved from the multi-core era is very, very hard to scale. As you can see on this plot, for the last couple decades, as core counts have risen from a handful to hundreds, thousands, chip makers have been abandoning these L1 caches in favor of software managed Scratchpad memories. And this has been pretty helpful for scaling, but it has come at a very heavy cost of programmer productivity. And I think it's good to take a second here to just think about why we liked coherent L1 caches to begin with so much. And, you know, it's not. It's pretty obvious, actually. Think about it. They reduce memory latency by orders of magnitude. They capitalize on reuse in software. And we can still get a lot of this from Scratchpad, luckily, but something we lost was an abstraction of memory uniformity. On a multi-core system, software can just access gigabytes of system memory. It doesn't really need to care too much about where that data lives, because hardware is working under the hood to make all that data seem coherent fast. It's actually pretty foundational to a lot of modern software engineering. If you don't need to consider hardware, memory as a first-class object, that's one big less reason to program in a low-level environment like assembly or C. Which brings us back to how do we program these 1,000-core systems that don't have any cache? A major concern is the exposed memory hierarchy. Unlike multi-cores where you have virtual memory, L1 caches, coherence to make all the memory seem coherent and quick, you don't really have this on a Manycore. Instead, you have an exposed memory hierarchy, and this is usually done in the form of a partitioned global address space, which is a memory model in which addresses map to physical elements on the chip, such as a specific core, an accelerator, or an off-chip memory module. And this can have very big latency implications for software. On the example of Hammerblade, which is the Manycore that we target, each core is co-located with 4 kilobytes of Scratchpad, which is a 2-cycle latency to access. On the other hand, if you want to access the abundant shared memory that exists off chip, that's on the order of 70 to 300 cycles. Another key thing you can do on Hammerblade, and this will come into play later, is that cores can access each other's Scratchpad memories, which the latency for which depends on their relative distance on the chip, but this can be as fast as 5 cycles. And this is all just to say that software needs to carefully consider the latency hazards of every single memory load and store. Another thing that makes these systems very challenging to program is the programming model itself. The most common method for programming these massively parallel systems is single program multiple data, in which programs are expressed in terms of bulk synchronous parallel regions, and control flow is expressed using IDs and barriers, such as the example here shown for vector addition, where you have the thread ID and the sync call. And this is fine for embarrassingly parallel applications, but for other state-of-the-art parallel algorithms where the control flow is more complex, or they might be grappling with issues like load balancing, this is less than ideal. And actually, this programmability challenge is a major hurdle to the adoption of these otherwise very promising systems. So to tackle this problem in this work, we decided to take a page from the Manycore in the form of the task parallel runtime environment. In this environment, programs are expressed in terms of smaller tasks that can be executed in parallel. As the program executes, new tasks are spawned and a dependency graph is formed between children and parents. And a key part of this programming model is the load balancing engine, which comes in the form of work stealing. So we looked at this and we thought, well, this would probably a good fit for our Manycore if you want to express some of these more complex algorithms. But the conventional thinking is that to make something like this work, there's a lot of shared data structures that need to be coherent, and without these coherent LON caches, the overhead would just be too high. And in this work, we wanted to explore if this thinking was true. We wanted to see if indeed the overheads were too high, and if they were, could that performance gap be closed with clever uses of the Scratchpad memory? So how do we build this? Well, basic element of this runtime is the task object itself. These are the work items that can be completed in parallel. Each one has a reference counter, which is the number of uncompleted children, a parent pointer to which the child updates atomically when it completes, and a virtual execute function that user-defined subclasses can override. And each core owns a deck of task objects. A key function is spawn. Software calls this to detach a child task from the parent thread of execution. What happens when a spawn is called is the core will push this child task to the head of its local core deck. And then there's wait, which a parent will call when it needs to wait for its children to complete. It has a reference counter. And when it calls wait, it will wait for this to turn 0. And in the meantime, it will look for more work. In the first place it will work is the head of its own deck. If that doesn't work, if there's no work there, then the core becomes the thief. And it'll start looking for random victims in among the other cores in the system. It will steal from those in FIFO order. So the first tasks that were put in will be the ones that it steals. All this would work great on a multi-core system because the memory system would work together to keep everything fast and coherent. On a Manycore, we have no such luck. So what do we do? Actually, as a baseline approach, we just do the same thing. We don't expect the peak performance, but we can at least get some benefits of the load balancing. But we also want to explore some of the benefits that we can get from Scratchpad memory. The first optimization we looked at was placing the stack in Scratchpad. And this has some pretty obvious benefits, namely that a lot of stack allocated data is compulsory in software. Something that needs to be considered, though, is that these tasks can move. So, and they can also reference their parent frame. So in the case of this fib example, we can see that 2 children respond that update X and Y is allocated in the parent frame. But suppose one of those children gets stolen. It needs to update X, but it's executing on a different core. What we learned here is that an enabling feature of hardware is globally addressable Scratchpad. This allows us to store the stack pointer as a globally addressable Scratchpad pointer, and that means that parent frame pointers will remain valid as tasks move around the system. This is opposed to locally addressable pointers, so ones that are maybe dependent on where you're located in your execution. Another thing we looked at was putting the task queues in Scratchpad. This is helpful because in the common case with these parallel runtimes, cores are actually only accessing their own deck. So putting in Scratchpad, making the latency 2 cycles instead of 50 to 300 accelerates the common case. Additionally, thieves are now able to steal from the victim Scratchpad directly, which reduces pressure on the global shared memory system. To evaluate our work here, we had 2 questions that we wanted to answer. 1, were the overheads of this work stealing runtime too high? And 2, if they were, could we close that gap with clever uses of the Scratchpad? To do this, we used 6 design points. First, we changed up the scheduler, so we had a static scheduling version of our runtime, so one in which each core is just assigned an iteration of a parallel for loop, for example. In there, we compared using the stack in Scratchpad versus having it in DRAM. And for work stealing, we checked one where we didn't have our optimizations enabled at all, one where we have the stack in Scratchpad, one where we have the queues in Scratchpad, and finally one where we used both optimizations. Example here for matrix multiplication is shown. What we found is that work stealing never really diminished the performance by more than 10%, and those were on the embarrassingly parallel applications, which we believe would have done just fine in a SPIMD environment. But we also found that it can improve the performance by more than 3x. We also found that by applying our Scratchpad optimizations, we could close any of these performance gaps. So just to wrap up here, I want to leave you with some parting thoughts. We wanted to solve the Manycore programmability challenge by taking this task parallel programming model and applying it to the Manycore system that we had. And we wanted to know, were the overheads too high despite the memory system not having any L1 caches or any coherence? And if they were, could we close that performance gap? And what we found was the overheads are okay, they're not so bad, even with everything in DRAM. The worst case was on the order of 10%. But we also found that having this kind of runtime could help by more than 3x on some of our more unbalanced algorithms. We also found that the overheads were very much offsettable with Scratchpad memories. Together, using both the stack and Scratchpad and putting the task queue management in Scratchpad, we could get a 25% improvement. This led us to conclude that the task parallel model is indeed a valuable and promising general solution to the Manycore programming challenge. Now we're ready for a 4 million core system. Thank you very much. If you found this interesting, please come check out our paper. DOI is posted. If you want to talk more, come find me in tomorrow's poster session. Thank you.